Okay, let us go with improper integrals. It is the last part. It is the last part. So what is an improper integral? This is just a short introduction. An improper integral is an integral that deals with unboundedness. So first we studied Riemann's integral. That means you have a bounded function on a bounded interval, perhaps discontinuous, but this is not important. And you have to compute this area. So you have here a bounded function on a bounded interval. So improper integrals removes these two limitations, the bounded function and the bounded interval. So here you have, for instance, so first type of improper integral. For instance, this. Consider a function, for instance, e to the minus x. On the interval 0 plus infinity. So we will study first bounded function on an unbounded interval. And the second will be to study for instance, think of 1 of square root of x here. On the interval 0, 1. So the second kind, unbounded function. On a bounded interval. And the third will be also an unbounded function. On a bounded interval. On an unbounded interval. And of course, we will study in detail the first case, and then the second will be just, if you want, a rotation of the first one. But however, the result will be the same, and the third is just the union of the first two techniques. But one can also ask why. Why to study these strange things? And the idea is that, of course, when you compute the area of a finite region, you can imagine as an application that you have a wall, a bounded wall. Okay, so you have to know how much paint to buy, very, very roughly. And so it is much stranger if someone asks you to paint an infinite wall, infinite in the sense that unbounded. Okay, unbounded means there is no square, there is no rectangle if you want, there is no circle that contains all the region that you want to paint. So the first answer that can come up to your mind is that it is impossible. You don't have such a possibility, because you should buy an infinity of quantity, an infinite quantity of paint. But you will see that it is not really true. So it is impossible to associate a finite area also to some, not always, not all to some unbounded region. And so you can easily see how to do it, but we will see in the next lecture. This is just a sort of conceptual introduction, and I want to tell you just a few things. First, so imagine that you have to paint an unbounded wall. Do you really need an infinite amount of paint? So this is the first question. This is the first question. And the second, some examples. So the problem is compute the area between the x-axis and the graph. Today I'm horrible. And the graph of the function f of x is equal to 1 over x squared in the interval (1 plus infinity). So it is a strange question, so you have to reason a bit, and the idea can be the following idea. Compute the area of such a region, but not between 1 and plus infinity, between 1 and some c much larger than 1, very large, and then see what happens. What do I mean by see what happens? Okay, let me explain it. Okay, from 1 to plus infinity, so you start from here to 1, and then you go in this way. It is not a hyperbola, but it is something less. It is below the hyperbola 1 over x. This is 1 over x squared. And then you fix c. Imagine this c to be very far away. So you first compute this area, which is the integral between 1 and c of 1 over x squared. You know how to compute it, and this is minus 1 over x between 1 and c. So you have minus 1 over c minus 1. So, sorry, plus 1. So this is c minus 1 over c. Is it correct? Yes. And this is very interesting. So notice that regardless of the size of C, so even though C may be 1 billion, 1 trillion and so on, may be extremely large, so regardless of the size of C, the area always remains bounded by 1. C minus 1 divided by C is equal to 1 minus 1 over C, so it is less than 1. So, therefore, when you push C, let me say, very far away, the value you find, the area, will never blow up, will never explode, will never diverge to plus infinity. This is a qualitative reasoning, but it can be made rigorous by introducing the idea of limit, as usual. The limit for C going to plus infinity. So, the limit for C going to plus infinity, which means that here C is pushed very far away, and this is the most intuitive and natural idea of painting all this wall here up to plus infinity. So this limit of the area between 1 and C of 1 over x squared equal to the limit for C to plus infinity of 1 minus 1 over C is equal to 1. So this is the most intuitive idea of area from 1 to plus infinity below the graph of 1 over x squared. And it is not unbounded. It is 1. Then we are authorized, morally, we are authorized to define whatever we want in mathematics, but it must be useful. So we are authorized to define the improper integral 1 plus infinity dx over x squared is equal to 1. And this is exactly, this is the only idea we will use for improper integrals. Okay, but then there will be some techniques and there will be some other ideas, because it is not only true. On the other hand, this is not whatever, it is not what happens. In all cases, if we want to compute the area below the hyperbola, 1 over x between 1 and plus infinity, we can do as before. So we go from 1 to c, and then we push c to plus infinity. Of course, this is log of absolute value of x, but here we are in the positive half axis, so this is the limit we are interested in. So this is log c. Sorry, this is the limit for c going to plus infinity of log c, and this is equal to plus infinity. So in this case, and it is extremely subtle, in this case what we have, this is the hyperbola 1 over x, and this area is plus infinity. Here we have the hyperbola 1 over x squared. Start from here, the same. And this area is 1. That's amazing. But so we need a somewhat deeper analysis to understand first when an unbounded area, an unbounded region has a finite or infinite area. And this is the main task of the next lecture, on the next video. Bye bye, see you.